Alright, so this video is going to introduce us to section 5.3, which is on the first part of the fundamental theorem of calculus. So we're going to learn two parts. This video will be about the first part. We'll take time in class to practice this first part, and then the next time we'll come back and talk about part 2. So the big idea in this video is to introduce you to the fundamental theorem of calculus, talk about how amazing it is, and work some examples. And then in class, we'll go through the proof of this theorem and talk a little bit about why it works, because it's so amazing that it does, and also work a few more examples together. So the fundamental theorem of calculus, this thing is amazing. It is so amazing, and you're hopefully going to be amazed. But what it says is if we take a continuous function on an interval from a to b, and we take the integral from a to b of f of x dx, which hopefully you remember that for us that's representing area under the curve, right? Or a net area, change in area. So the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where f is the antiderivative of f. So in other words, the capital F prime is equal to f. So here we're relating area, right? This is an area function. We're relating area under the curve to antiderivatives. So that thing that we did back in section 4.9, right? We're now saying that the stuff that we're doing, area, is essentially the same as what we did in section 4.9. And this is amazing. You should hopefully think this is amazing. It may not seem amazing because we were using that word antiderivative over there, and we were also using a symbol of an integral symbol for those indefinite intervals. So it may not seem amazing, but hopefully when you look at the proof of this and see where it came from in class, you'll recognize how cool it is that this thing that we've been talking about, area, right, this net area function, can actually be represented and go back to this calculus idea of antiderivatives, which is really, 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 really cool. So let's look at some examples. First, maybe some notation of you'll see questions like this. So in other words, the fundamental theorem of calculus is saying that if we integrate from a to b of some function f of x, that we'll get the antiderivative of that function, and then we're going to plug in a and plug in b. So that's what happens when you integrate. This integral is telling you to integrate with respect to x, so that part, those two things go away, and you're just left with the antiderivative, and this symbol here tells us to plug in b and then plug in a. So in other words, you'll get f of b minus f of a. So we have 3 examples here to talk about and see what happens when we take their when we integrate. So we know how to find the area under the curve. We know how to do it with that limit definition. But now it's saying, hey, all we have to do to find the integral from 0 to 3 of x squared is find the antiderivative of x squared, which hopefully remember is 1/3 x to the third. We ignore the plus c because we just want one antiderivative of this function, because what we're going to end up doing is subtracting off those c's. So you could put the plus c here, it's not really incorrect, but if you think about this, we're going to plug in 3 all the way across, and then we're going to subtract where we plug in 0 all the way across. So if you have a plus c in this first function and then subtract the plus c, the c's will cancel. So when you're doing this, what's known as a definite integral, right, that's what we've been doing, you don't need the plus c. Indefinite integral, you will. But here's this. So then this, all we're going to do is plug in a 3, and then plug in the 0. And if we work all that out, it looks like we'll get 9. And that is the indefinite integral, or the definite integral from 0 to 3 of x squared. In other words, the area under the curve from 0 to 3. And so we're now able to use calculus, right, to do that, as opposed to just taking areas under a curve, which is pretty awesome. So next, it wants us to find the integral from 3 to 5 of sine of x to the 4th dx. And unfortunately, if we start to try to do this and we think about, hey, we need the antiderivative of sine of x to the 4th, we actually can't do that, right? I don't know the antiderivative of sine of x to the 4th. So it's just kind of a cautionary tale of, since I don't know the antiderivative of sine of x to the 4th, I actually can't use the fundamental theorem of calculus. And so I can't do this question. So we just leave it as a question mark, and it's not one that we'll know how to do, nor that one that we'll really be able to do by the end of the semester. So we just skip that one and say, well, we hope we could do that, but we don't have the right integration techniques to be able to do that. And then this last one, we want to integrate from -1 to 1 of x to the -2 dx. And you might start doing that and saying, okay, I can take the antiderivative, add 1, right, x to the -1, divide by my new power, -1. But be careful here. You have a big problem here. X to the -2 is not continuous on the interval -1 to 1. And if you look back at our fundamental theorem of calculus, if you look back at it, you'll see, right, the function has to be continuous on the interval a to b. So in this case, right, we are not continuous. It's not continuous at 0. And so we can't actually do the fundamental theorem of calculus here. So again, we can't actually end up working either of these last two examples with the fundamental theorem of calculus. It does have some restrictions, right, but we are able to do the first one there. Okay, so I do have another example here just to practice with these definite integrals with using the fundamental theorem of calculus. So here's one. When you first look at it, I don't know how to take the antiderivative of this thing as it's written. We haven't talked about how to take antiderivatives of fractions. But remember, when we are doing antiderivatives in section 4.9, it's always easy to simplify these and write them as something that maybe we can actually integrate. And in this case, it looks like I can split that into two pieces and then rewrite. That first one is x to the -1/2. And then here I can subtract exponents. That's x to the 1/3 over x to the 1/2. And if I subtract those exponents, it looks like that will be x to the 1/6, I believe. And maybe it's negative because the denominator has a larger value. So if I subtract these, right, that's x to the 1/3 minus 1/2, and that's 2/3 or 2/6 minus 3/6, so -1/6. Okay, so that's simplifying these two things down, and now I can take antiderivatives. Remember, it's x, and I want to add 1 to this exponent, so that becomes positive 1/2. If I divide by that new exponent, dividing by 1/2, remember, is the same as multiplying by 2. And then similarly here, if I take x and add 1, I'm going to get 5/6. If I divide by that new exponent, 1 over 5/6 is the same as 6/5. And I want to evaluate that from 1 to 64. So that means now using the fundamental theorem of calculus, remember the dx and the integral sign, those go away as you integrate. So from here to here, I did the integral, I took the antiderivative, that was the fundamental theorem tells me to do. So I took the antiderivative from here to here, and then now I just have to plug in my two bounds. So I'm going to plug in 64 all the way across first. And then I'm going to subtract if I plug in 1 all the way across. So it looks like I'll have 2 times 8 plus 6 over 5. I believe 2 to the 6th is 64, so this is going to be times 2 to the 5th. And then minus 2, and then minus 6/5, being careful with my minus sign and making sure I distribute it. And so if I work all that out, I don't know, 16 minus 2 is 14, minus, I think it's 31 times 6/5, or plus, probably plus. And then whatever that's equal to. I didn't work all this out, so 14 plus 186 over 5. So you can get that final answer probably by just adding those two fractions together. You could put it all over 5, I guess. You could make this, whatever that would be, 70 over 5. So you can get maybe 256 over 5 if you work all that out. You should be a little bit careful there of my addition, but I think it's 256 over 5 as your final answer. So the idea is to first get it in a form that you can take the antiderivative, and we only have a few antiderivatives we can do, so you won't have too many different types of questions that look like this. Then we want to simplify it so we can actually take the antiderivative. Antiderivatives, we add 1 to the exponents, we bring down the new power, but we bring it down as the reciprocal because it's 1 over the new power, so we have 2 and 6/5. We plug in 64 all the way across in our question, and then we plug in 1 all the way across in our question. We subtract those two values. Notice the importance of these parentheses. These are very important to keep track of that minus sign. And then we just evaluate. 2 times 8 plus 6/5 times 2 to the 5th, and then minus 2 plus 6/5. But the two minuses just distributed, you have a minus 2 and a minus 6/5. And assuming that I can actually add on this thing without thinking about it, we get 256 over 5. So one last thing is just making a quick note about the difference between an indefinite integral and a definite integral. So the definite integral, those are the ones that we've been doing in this section. Remember, it represents sort of a net area. And so you will in fact get a number as an answer. Okay, so those are the things that we're doing. We're calculating a net area, we're getting back a number. But remember, these are indefinite integrals, so these are indefinite on this side. And then over here we have our definite integrals. And remember, the indefinite integrals, those are a family of answers. So those are the ones that have the plus c. So the slight subtle difference, indefinite will have the plus c. The definite will have a specific number as an answer because you're going to evaluate all the way across that definite integral. So just reminding, here's the general indefinite integral example. To remind you of the indefinite integral just means to take the antiderivative. So if we have this function 1 minus t, 2 plus t squared, again, we don't have a way to integrate multiplication. So we're going to need to distribute all of this stuff. So we're going to get plus a t squared minus a 2t minus t cubed. So now we have all that distributed. We're just going to take the antiderivative. That's what that symbol means. So 2t plus 1/3 t cubed minus 2t over squared over 2, and then minus 1/4 t to the 4th. And because this is an indefinite integral, right, there are no bounds, we're going to tack on that plus c. And so if you want to make this look a little bit nicer, 2t plus 1/3 t cubed minus t squared minus 1/4 t to the 4th plus c. Okay, and those are the differences. Indefinite integral, we're going to get a specific family of functions with the plus c. A definite integral, we don't have to add on the plus c because they'll cancel as we make the subtraction according to the fundamental theorem of calculus part 1. We'll practice more examples in class and see how we feel about this first part of the fundamental theorem of calculus on next time.